What we're going to do today is we're going to look at a little more complicated types of rational expressions, and we're going to do a thing called horizontal asymptotes as well as vertical asymptotes. They're a little harder to follow. I'm going to try and explain them as well as I can. I'm going to do f of x or y. I guess I can use y in this one. Y equals, you may want to use another paper, depends on how much room you got. We're going to do 2x minus 5 over x plus 2. This is called a rational equation or a rational function because it has a ratio. That's where the word rational comes from. What value of x gives me a problem? Negative 2. X cannot be equal to negative 2. Wherever I have a problem with x, I have a vertical asymptote. So I'm going to write that down. My vertical asymptote is at x is not equal to negative 2. I don't want to write things that aren't true, right? X will never be negative 2, so I'm going to write x is not equal to negative 2. Everybody see I'm dashing this line? I can't cross that line. If I cross that line, it means that my function would be equal to negative 2, and I'm not allowed to ever be negative 2. It's like a limit. This line is a place where this function can't ever go. It can get really close, but it can't touch that line. You guys played that game before. Sit in the back seat. I'm not touching it. Yeah, right? If you have brothers and sisters, you know what I'm talking about. Especially younger ones. All right. We're going to look at a thing called the horizontal asymptote. This is the one where you're going to have a little trouble. I want you to imagine that we're going to pick big number for x. Nice big number like 1,000,000. Do you really care whether they take $5 off the price if you're paying $1 million for a car? You really going to sit there and argue with them about $5 one way or another? Probably not. This 5 has almost no effect on 1,000,000. Neither does this 2. Does that make sense to everybody? So what I'm going to do is when I look at really large values of x, this has almost no effect. What is 2x over x when you divide it? 2x divided by x. You get 2. In other words, if I put 1,000,000 in here, don't I basically get 2 million over 1,000,000? Yeah. Divide that. 2 million divided by 1,000,000 is 2. 200 divided by 100 is 2. Basically, you get 2. The bigger the x is, the closer you get to 2. You never quite get there, though, because this messes you up, doesn't it? So here we go. This is called end behavior, and y equals 2 is my horizontal asymptote. It's what happens when x gets really big and really small. 1, 2. When x is really big, I get really close to 2. Yes?
Can you give this to the bottle?
Yeah.
Thank you.
By the way, this equation is x is not equal to negative 2. What's this equation of this blue line here? What's the equation of this blue line? What's not equal to? Y equals or not equal 2. Yes? Isn't this y equals? This is x equals? Why do I write y equals 2? Look at what happens when x is really big. What do you get? You get 2, more or less. Y equals 2 when x is really big. This is y equals 2. You got it so far? All right, you're going to have two more things that you got to think about. They are your x-intercept and your y-intercept. When you all took all through this courses that you've been taking in math, they've been telling you that the x-intercept and the y-intercept were numbers. They're not. That's wrong. The tax test is wrong. The x-intercept and the y-intercept are not numbers, they're points or ordered pairs. You need to write them as ordered pairs. They've messed you up a lot, but we'll fix it. The y-intercept is the value, or rather the point, where the graph crosses the y-axis. It's an ordered pair. What goes in for x? 0. Substitute 0 for x and see where you're at. Look at what happens when x is 0. Negative 5 over 2. Where is that? Where's negative 5 over 2? Another way to write it. Negative 2.5 or negative 2.5. Makes it easier to graph, doesn't it, than a fraction? So graph negative 2.5. 0, negative 2.5. So you're on the y-axis. It's a y-intercept. Now graph your x-intercept.
0.
What's 0 for the x-intercept? For the y-intercept, x is 0, right? So what's the 0 for the x-intercept? The y is 0. The x-intercept looks like this, doesn't it? And it's on the x-axis somewhere. What do I want to be equal to 0?
Y.
I want y to be 0, and I want to find out what x is. We had a name for this. It was called a root, wasn't it? Or a 0? What will x be to make this 0? We don't want a 0 in the denominator. We want a 0 in the numerator, don't we? What is it? Positive 2.5. Yes? Think about y. With positive 2.5 in here, what do you get? You get a 0. That is a 0 or a root or an x-intercept.
Because of the 5 up there.
Well, because if 2x minus 5 equals 0 and you solve it, you get 5 over 2. That's 2.5. It's right here. Now we know that we're going to have curves, right? Everybody follow that we're going to have some curves here that approach these lines? Since we know that this point and this point are on here, chances are that our curve is going to go down here. Yeah? So I'll follow that? That if these are our asymptotes, then this curve goes and gets closer to here, this curve and goes and gets closer to here. But there's a way to test that. What I can do is I can do what we call approaches. I can look at what happens to x when I approach negative 2 from this side. If I take x and approach -2 from the positive side, I'm looking at numbers that are just a little tiny bit bigger than -2. What's a number that's just a little bigger than -2? -1.9 maybe? So I'm going to pick a number like -1.9. Now look at what happens. To tell you the truth, I don't care what the value in the numerator is. I just care whether it's positive or negative. And you'll understand why in a minute. What do I get in the denominator when I add 2 with -1.9? Positive 0.1? I only care that it's going to be really small and positive. It's going to give me a small positive number, and in the top, aren't I going to get a big, just a negative number? I don't care how big it is. It doesn't matter. What matters is that as this number gets close to -2, like -1.9999999, doesn't this number get really, really, really tiny? And that makes this division huge. All I care about whether it's going to negative infinity or positive infinity. Since this number is going to be negative, I don't care what it is. Doesn't matter what it is. It's going to give me negative infinity when I get close to here. That's a really tough idea, those approaches. It's like this. And it's going to get closer to -2. It's going to get close to -2, really, really close, and it's going to get huge and negative, because this number's negative up here. And this way, as x gets really, really large, it's going to approach to this line, y equals 2. Because when x gets really big, we don't care about those. And this is 2. Over here, we're probably going to be inside of this area right here. In between these two, we're going to get a curve in here somewhere. A good idea might be to pick a number like -3 and see if it's in here somewhere. Put -3 into this and see what you get. Actually, positive 11, yes? Don't you get a negative in the numerator? -11 up here, and a -1 in the bottom? Does everybody see I'm going to get positive 11? It's going to be way up here off my graph, but basically, it's going to do this. Now later, we could actually test the numbers. Does everybody understand that if I go from the other direction here, look at this. This time I'm going to approach -2 from the left. We write it like this. X is going to approach -2 from the left. It's going to be a little smaller than -2. Does everybody see that I'm going to get a small negative this time? And that this is still going to be negative? And a negative divided by a negative makes positive infinity. A lot of thinking involved in these.